Hi everyone, I would like to show you how to use MATLAB to fit curves, and I will explain the procedure by using 3 different examples from one-dimensional to three-dimensional cases. Let's go to the first one, one-dimensional curve fitting, which is the probability curve fitting. Imagine you have a statistical distribution of some variables. For example, in our case, we have the grain size distribution, which is obtained by performing some metallographic investigations, and we measure the grain size over 3 different grains. And here is the grain size results. And how can we use MATLAB to get such a smooth grain size distribution function? And of course, we can use different functions, the log normal and gamma and kernel distribution functions, and I will show you the procedure. First, in MATLAB, you need to create new variables. In our case, we call it grain size. For example, error. And then I copy this experimental data and paste it here. Then I go to apps and click on the distribution filter. Then you click data to create a new data set. Select this grain size error and it looks like that. Create data set, and you can rename your data set if you like. So close, and then you can create a new fit, or you can do it by manage fits. First, create a fit. Let's do the log normal curve fitting first. This is the data, and you choose a different fitting function, log normal, and then you click apply. So it will automatically give you the mean value and this variance. Close. And so this red curve is the log normal distribution function. And then you can create a new fit. Let's take it the gamma distribution function as examples. And you select gamma function, apply, close. Here it gives you this blue curve, which is the gamma distribution function. The third case is the kernel distribution function, and the kernel distribution function is a non-parametric distribution function, and you can select whether the kernel is based on normal distribution, box, triangle, and so on. So we take the normal in our case and click on apply. So here is a new curve, which is the kernel distribution function. You can switch off. This is the kernel distribution, and that's it. So then you can print to figure and click this button to a fixed window. Then you can change the X and the figure properties. For example, you can increase the font size, the X name, and so on. So this is the first case. Then you will get this smooth probability distribution function and also with the calibrated parameters. The second case is the two-dimensional cases. I call it two-dimensional because we have a X variable and Y variable, which is the strain and stress. In our case, this is the flow curve fitting for metallic materials. For metallic materials, we can perform, for example, tensor test to get this stress strain curve until uniform elongation. For example, in our case, it's 0.3. So this black dot corresponds to experimental data, but beyond that, we cannot get this information by performing experiments. Therefore, we need some mathematical treatment to extrapolate our experimental data. And there are many different functions to extrapolate these experimental flow curves. For example, there are Hollimon, Ludwig, and so on. And today I will use this Swift hardening equation and show you the procedure to fit Swift hardening parameters. So we have two variables in this equation, sigma and epsilon, and we have three different parameters in this equation. So the procedure is more or less similar. We have to create two new variables, strain and stress. I already copy-pasted the experimental data. What's different here is we click on curve fitting. And then you write this fit name, we call it flow curve fitting. And then you select X data, which is strain, and Y data, which is stress. Then you can select which functions you would like to use. You can use polynomial. For example, if you have a first degree, then it is a linear function. It's not working well. And then you can increase the degree. For example, when it gets to 3 degrees, it's already good enough. And today I will use this custom equation. And I will write the equation for this Swift hardening law, C. So it is C1 times X plus C2 to the power of C3. Alright. So it says cannot get these coefficients, and then you can click on fit options. You set the boundaries for these parameters. These parameters have to be positive in our case, and you can give a initial guess. For example, based on the previous experience, I know 600 is a good example for these parameters. And now you can change the xy limit from 0 to 1 and take it from 400 to 600. And then you can go to print figure. So here you can change the figure quality, increase the symbol size. So that is the second case. And in the third case, I will explain how to use MATLAB for three-dimensional surface fitting. And I will take the example of this bi-Wisbicki fracture equation. And it is a very popular fracture model in damage mechanics. So it has three different variables. Epsilon, which is the fracture strain, in our case is the z-axis, and eta is the triaxiality, and z bar is the load angle parameter. So these three variables has a certain relationship, which is described by 4 different parameters, d1 to d4. And this black dot corresponds to experimental radars, and we want to fit a smooth fracture surface like this. So the procedure is the same. We create 3 new variables, epsilon, eta, theta, and then I select, change the name first, call it fracture surface fitting, and select x data, which is eta, y data is theta, and that data is epsilon in our case. Then we choose custom equations, and I have already written this equation here. So you just simply type in your custom equation, and let me set the x limit from 0 to 1 and y from -1 to 1, z from 0 to 4. So this is the fitted smooth curve surface, and it gives you these 4 parameters. And normally you will not get a r value equals to 1, it must be smaller than 1. But this value is not really experimental data. I created this value, but the procedure or principle is more or less the same. So print to figure, and here you can modify the figure properties. Okay then, so that is the MATLAB curve fitting tricks. I hope that helps you. Thank you very much.